So I would like to talk. What I would like to talk about is this reconstruction of modular data from the representation SL2C. So maybe I spell out the background first, and then I can tell you what the rationale is. Probably is clear from the title of the talk and also the paper. So let me just lay out the basic of modular tensor category. I assume most of you, if it's not all of you, know almost everything here, but I just lay out the language here. So a modular tensor category is just a fusion category over complex number in this talk, equipped with a non-degenerate braiding. I call it beta here. Non-degenerate braiding is a technical term, but you can think of the braiding as the double braiding as a bilinear form. Then the notion of non-degenerate braiding suddenly become more intuitive, and the notion of spherical structure. So spherical structure is indeed a gadget for taking trace of morphism. So I try to suppress this technicality, but at least we have this in our mind that we have a braiding and spherical structure, and the spherical structure together with the braiding give you something called the ribbon structure. So which is a isomorphism of the identity functor. And this ribbon structure, in fact, these kind of category used to be called a ribbon category. But I think the ribbon if you use to know ribbon category, these notions is equivalent to say is a braided spherical fusion category. So instead of using the word ribbon category, I just define the ribbon structure using the braiding and spherical structure. And the set of isomorphism class of simple object is denoted by IRRC, irreducible object. The unit object 1 is always there by definition of fusion category. And for any irreducible or simple object in C, the theta x is actually a scalar multiple times identity by using the Sewell lemma or the definition of fusion category. So we usually denote the scalar also by theta x. So the theta x is two meaning here. One is the one meaning is the morphism, and the other one is scalar of scalar multiple or the identity. So, but I think in general it won't be confusing, but at the beginning it may be confusing. So modular data of C is a pair of matrices indexed by the irreducible object, which define its following. So the S matrix, you just take the braiding. So you braid I star tensor J, and then you braid again J tensor I star. And then this is a double braid if you like to use the picture, but there's no need for today's talk. Then you take the trace means close the loop. So basically we do this. This is actually it's a number. So for each pair of simple object, you get a number. Then you put them together, they form a complex matrix. The T matrix is similar. You put the ribbon structure in the diagonal, the scalar in the diagonal of the matrix, then you get the T matrix. So it is the result of Waffer that T must have finite order for modular tensor. Actually, not necessarily modular tensor, but at that time, this is the result. And then S must be invertible. So the notion of invertible S matrix and non-degenerate braiding are equivalent, in fact, which is proved by Milger. So these results actually can allow us to define the representation of SL2Z, which is also called a modular group. So that's why we call it modular tensor category. We call it a modular group. SL2Z is the group of 2 by 2 integer matrices of determinant 1, and it's generated by these two matrices. I call this German S and German T. German S is the order 4 element, and the order T is translation by 1. So you can present the modular group abstractly using SNT. So namely, SL2C is generated as a free element with relations. So the element in SNT and satisfying ST raised to the power 3 equal to S squared, S to the 4 equal to 1. So you can replace these two presentation with others. If you replace, say, if you change S by S inverse, then the relation will be different, actually simpler. But for the purpose of this talk, and this is more commonly used in modular tensor category, so we stick to this convention of modular group, and S and T are the inversion of order 4, and T is the translation. So once you have a modular tensor category, you can write down the S and T matrix. You can make assignment. So this inversion of order 4 sent to the capital S, and this translation T sent to the T matrix of the modular tensor category. This assignment can extend to a group of morphism of SL2C to PGL and C. So this is actually a projective representation. Or the other way to say is S and T satisfy these relations projectively. So therefore, you have such projective representation. Now, this representation is canonical defined for any modular tensor category. So there's one thing which is not canonical, which is order of the simple object. So we ignore the ordering of the simple object. We ignore the ordering of the simple. So that means if you have one representation, if you conjugate a representation by a permutation matrix, we consider to be the same. In general, you can only say the equivalent, but in this talk and actually in our paper, we consider two representations differed by a permutation matrix are the same, basically. Conjugate by permutation matrix are the same. Now, so these are representations is canonical defined up to the ordering of the basis, but this is not very easy to deal with. But actually, it carries one information that is never been used in the paper and never mentioned in the paper. A projective representation involves a two co-cycle of some finite modular group. This is actually one of the invariant of modular tensor category, but it's never been used in the paper. Actually didn't mention, but it mentioned elsewhere. But anyway, nevertheless, we linearize it or we scale this matrix to mix it into a representation. Not the projective one, ordinary one. So these are different. This is projective representation. This is ordinary representation. Just by rescaling it. So rescaling the S and rescaling the T, you can rescale the S by the square root of the dimension and T by some third root of the central charge. Then you can get one linearization of the projective representation. So any linearization or any rescaling, any representation obtained by rescaling the S and T matrix of the modular tensor category are called MD representation here in the paper. MD really means modular data representation. This representation derived from the modular data for given modular data. So now the problem, there's one problem here. When you rescale this S and T matrix, you get more than one linear representation. So they're not equivalent. They are different by this. So if you get one, let's say rho C, the other one is simply tensor a one-dimensional representation SL2C to the one that you obtain. So all of these linear or MD representation of a given modular tensor category could be differed by a linear character of SL2Z. So this is a group isomorphic to Z12. So at most you have 12 inequivalent ones. Could be less. Depends on whether the tensor is equivalent to itself. So bear in mind that the MD representation for a modular tensor category is not unique, but unique up to a tensor factor of a linear representation. So I usually call it projectively equivalent because just divided by a scalar. So after this linear character, they are the same. Now, so now we have the background of like empty representation, and then what we want is if I have the empty representation defined by a modular tensor category, and then like from the point of view of representation, I don't really care the representation itself. We care about the representation type. So at this point, we only talk about representation type. But later you can see that whole thing is about a representation of finite group. So then we can just talk about the character of the finite group, and you can ask whether this character determine certain modular tensor category or not. So this is more or less a goal. Can we use the character of finite modular group to determine whether maybe it's a finite family or of modular categories, or is it empty, or it may not be realized? Or so to this end, we need some property of empty representation and the arithmetic property of modular data. So basically, these are the properties that we will use to work out whether a given representation SL2C is realizable by a modular tensor category. And from a computational point of view, you can actually implement for such a determination. So let's go through some of them, and then you see that there's some significance when we try to decide whether a given representation is actually realizable. So start with a modular data of an MTC. So there are some algebraic integer inherent in these modular data. For example, the dimension of C divided by S0I. 0 always denote the unit object. So this quotient is always an algebraic integer. And actually, it was known before Sij over S0j is also, and in fact, they know it's cyclotomic integer. They know it's cyclotomic actually. What they don't know is the conductor of this cyclotomic integers. It could be very large, it could be very small. It was not known at that time. So, so because these are algebraic integers, you can take an automorphism of absolute Galois group. Well, this all go back to Valenda formula. Basically, we're using each of these quotient Sij over S0j. Determine the character of the diffusion ring, or the representation ring, or the quadratic ring of the modular tensor category. So, and this is a character. So when you apply Galois conjugate, you still get another character. So therefore, you're permuting the objects in a sense of the simple object of the modular tensor category C. So you permute them in this sense. So therefore, each automorphism with Galois group provide a natural permutation on the simple object of C. It's natural one. So this is assignment from the absolute Galois group to the permutation group of the simple object. Now, this is actually the important result for implementation, or in also deduce whether a representation of SL2C is realizable. So before we did not know where the algebraic integers lies, but now we know that it's a result due to myself and Schoenberg. The S matrix is always a cyclotomic integer in this cyclotomic field, and where n is the order of the T matrix. So together you actually put a bound on this S matrix, and in particular, this quotient, now we know the conductor is indeed n, or the conductor is bound by n. N is the order of the T matrix. So if you don't know where they lies, then you cannot hard to set up an equation to solve equation. Now we know where it lies. You can actually do some solving equation when we try to find out these modular data is realizable or not. So another one which is automatic, the S matrix is symmetric and T is diagonal. So when you rescale it to get a representation, the representation is also symmetric in the following sense. The one is like the representation, the empty representation rho is unitary. It's proved by in the Edinghoff paper, and the symmetric is obvious because just rescale the S matrix of the modular data, and you rescale diagonal matrix is still diagonal. So what we call this type of representation SL2C symmetric. So the point is like we know that every empty representation is symmetric. Then you ask like, how can you characterize symmetric representation? So, and can we use the symmetric representation to discover a new modular data, for example? At the beginning, we don't know the answer of this question. In time, we learn a little bit. So we talk about it later. By itself, we cannot characterize the symmetrize which representation SL2C is a symmetric representative. But if we add some condition to it, we know how. So that turns to the next slide, which is the arithmetic property of the MD representation. So now MD representation is just like rescaling of the modular data. It satisfies more symmetry indeed, which is better than the modular data in a sense. So first of all, the representation itself, the MD is certainly factored through this finite modular group. So this is a finite group. So therefore, each MD representation is a representation of a finite group. So now everything is over complex number. So the representation must be completely reducible. So you can write down into direct sum of irreducibles. And you know that the level is given by the T matrix, rho T. So moreover, this representation, the MD representation, it's defined, whole thing is defined over the cyclotomic field of order M. M is the exactly order of the T matrix under the image of rho. So again, you can do, now we don't need to do the Galois automorphism of Q bar because it's big, it's infinite. So, but then we can deal with the finite Galois group. So we know that this one is actually isomorphic to CM star. So we know what that is. So we can, so we suddenly our job is easier when you know you're going to deal with the finite group. So in the paper, Cox and Gannon, they actually define something called a D rho sigma. Basically, if you apply sigma to this MD representation S on S, then it will be given by a sign permutation matrix, D rho sigma times rho S. If you apply so how do you define this sign permutation? This permutation is given by the permutation that you saw before, but you can also realize by the representation. So same representation that you saw for the by using the modular data S to obtain, but you can also get it from the representation for the image of S. But what was not known was that in the paper, and in fact in the next 20 years, they did not know the image under the image of T under sigma square. In fact, they conjecture it. It's given by this formula. So this one play a role in the implementation. So basically, we know how sigma square when they apply to the image of T for MD representation, they're basically permuting the entry, diagonal entry, according to the sigma hat defined by this formula or the formula for the S matrix. So they tie together. So this become another arithmetic rigidity or property to decide a MD representation or given representation, whether it's MD representation or not. So now we know that we're dealing with congruence representation basically, and then we know that every MD representation can be written as a direct sum of irreducible factor of the congruent modular group. So now we would like to know the reverse. That means if you try to decompose such a representation, what do you see here? Or the other way around, if you try to put two representation SL2Z together, when is possible to form a genuine empty representation? So this is a criteria developed by a previous paper by Boudet, me, and Eric Rowell and Zhenghan Wang. Basically is that if you have an empty representation, you try to decompose it into direct sum, then both of them are representation modular group, but they could have different level. Anyway, but their spectrum, the T matrix is both of them are diagonalizable, so they have a spectrum. Their spectrum, the intersection of these two spectrum cannot be empty. So that means if you decompose the empty representation in three components, they have to satisfy three property given by this criteria. So this is actually a criteria very useful. It's not very difficult to prove either. So we call it like a T-spectrum criteria. So the first criteria need to be satisfied by the sum of two irreducible representation to be realizable by a modular category has to satisfy this condition. So if they don't have any overlap, they will never, the direct sum will never be an empty representation. So the one application that you can see is like, okay, can the empty representation be direct sum of one-dimensional representation, and the empty representation is dimension bigger than 1? The answer is not possible, because if it's true, according to this T-spectrum criteria, all these one-dimensional representation are the same actually. End up you getting a S matrix, which is a scalar multiple identity. So that will never happen, because the S matrix must have a non-zero row which represent the dimension. So this is one of the reasons for, well, this is one of the application, immediate application. The other one is like, this is also developed in the paper. It's like myself, Eric Rowell, Zhenghan Wang, and Xiao-Gang Wang. Basically, if you have start with empty representation, the decomposition could tell something about the underlying tensor category. So if an empty representation of an empty C of rank bigger than 2, 2 is the borderline, whose irreducible summand all have dimension less than or equal to 2. That means I just have 1 or 2, they put together. Then this empty C bound to be integral. So I cannot tell what they are. It may not be even realizable if you randomly put some 2 and 1 dimensional representation. But if you start from the other way around, if you start with empty representation of the dimension bigger than 2, you decompose it and find that all the irreducible summand can only be dimension 1 or 2, then this MTC bound to be integral. Now, the other one is like pretty easy to obtain. Again, developed in our paper. If rho is equivalent to an empty representation, rho is arbitrary one, arbitrary representation SL2C, which is equivalent to an empty representation. Then first of all, the trace of rho S squared cannot be 0, and because trace of rho S squared, well, rho S squared is sign times the charge conjugation matrix. So the absolute value of the trace of S squared is the sum of the self-dual object of C. So we know that the unit object is always one of them. So therefore, we always have non-zero. So this provides another condition for an empty representation. So not any representation of SL2C or even modular can be realized. A lot of them cannot be. The problem is which one can be. So this is still unknown. So now I lay out some background and result. So the goal is that if you start with a finite modular group, let's say SL to Z mod M, and then you have a character of this finite group, irreducible, or even just character of this finite group, can this character be realized? So if it can be realized, how many of them are there? So this is the question that we would like to address. And in general, we still don't have a very efficient theorem that tell, okay, this character can never be realized. Or another theorem is which this character can be realized. So we don't have such a global theorem. What we have is like, it worked for rank 6, rank 7, rank 8, and so on. So it maybe in time we can have some general result. At this moment, it just by experience it works. So we need to systematically label a modular tensor category in terms of the representation, in terms of its MD representation. So we define the notion of type. So let's say I start with MTC, and we call it like type D1 up to DL. If the corresponding MD representation decomposes into a direct sum of irreducible representation of dimension D1, D2 up to DL. Let's say I order them in a decreasing order. So the largest irreducible representation will show up the first. So this is one way of classifying a modular tensor category. It's very rough, but at least if we start with something. So let's take a look at some example here. For example, you have Ising modular tensor category. So there are many of them. So we always include Galois conjugate of modular tensor category. So if you have one, you can always apply the Galois symmetry to get more. So looks like it always show up this way. So for example, Ising modular, they all have type 3. So here it doesn't say, oh, only 3-dimensional irreducible representation, but we don't know what level it is, what is the finite, what the finite modular group is. For example, Semyon and Fibonacci modular tensor category, they all involve the generate MD representation of dimension 2, and both of them are irreducible. So therefore, this type is pretty simple, 1 digit only. But if you look at the quadratic form modular tensor category, maybe by the way, if you look at the representation, these are the wave representation. So these are quadratic form. The underlying representation SL2Z is just wave representation. So if you take a look at this pointed modular tensor category or Abelian anyon, then you try to decompose it, then you get type 2-1. Now it's no longer single digit. Moreover, this is a prime. It's a prime modular tensor category. You don't have any even fusions of category. So you cannot have any decomposition there. So this is, but the type has length more than 1. So in a more general setting, if you look at the quadratic form of the Abelian group order P, and then when you decompose it, you see that this is the smallest irreducible representation SL2 CP. And this is the second smallest. So when you sum these two representations together, you get the wave representation of the modular group of this quadratic form on the Abelian group order P. So this explains the notion of type, but certainly it's not sufficient because it's like you could have different level, but they're the same dimension type. So we need to be more specific. So we add one more level of clarity to the definition. So suppose rho C is an empty representation of C. Now we pick an ordering of the root unity. So because of the spectrum, it just involves a root unity. So among this spectrum, we can define another order. So you first of all, you order the root unity, and then you can define the order of a sequence of root unity. Then among them, you pick the smallest one. Remember that for given C, I have 12 empty representation associated to it. I want to get the smallest one. So that's this just a convention. And if rho C decomposes into direct sum of irreducibles, let's say I decompose it in rho 1 up to rho L, then remember they still representation of the finite modular group. They all have a level. So the level basically this is like N1 up to NL. Remember we already defined a type D1 up to DL, so we just put them together. So D1 up to DL are the dimension type. So in decreasing order, once you fix them, then you can write down the corresponding levels. So D1 for the level N1, D2 for the level N2. So basically now it's a more a detailed classification of an empty representation. So dimension type and also the level type. So you put them together in such a way that I just all together call it type 2. So the first block is for the dimension, the second block for the level. So now we can re-examine the examples we talked about before, the Ising modular tensor categories. Before we already know is type 3, and now we add to the level, which is level 16. So in fact, all of the Ising modular tensor category are type 3 level 16. Similar to the Ising one, which is semyon, which is type 2 is level dimension 2, but the level is 8. And all these representation type actually can be realized by semyon, or some kind of semyon. There, you can always do the Galois conjugate and get the other one. There another variation is some modular tensor category. This is as actual result of a Muir. If you have a non-degenerate braiding, then you can take whatever spherical structure, then you still get a modular tensor category. That means you still can write down the modular data. So in addition to the Galois conjugate, you can also get new modular data by using another spherical structure. So far, they usually, for example, in this case, all these like Ising tensor category of this type, and all the Galois conjugate, and also replacing the spherical structure of this type. So to have a new spherical structure, you need an object which has the dimension 1, forbidden dimension 1. So if you don't have it, there's only one that you have. So the choice of a spherical structure is not always there. Sometimes it's unique. Maybe look at for semyon, you do have a choice, and also Ising modular tensor category, you have two choices actually over them. So for the Fibonacci modular tensor category, the type is 2, the dimension 2, but the level is 5. And in fact, if you have a modular tensor type 2, 5, it's bound to be a Galois conjugate of the Fibonacci modular tensor category. That means you take the Fibonacci, you apply the Galois conjugate, you still get the type 2, 5. Usually they define the whole Galois conjugate and also the replacement of the spherical structure. And for this one, the one that we mentioned before, the wave representation of the quadratic form CP with quadratic form Q, the type is, we write the dimension before P plus 1/2, P minus 1/2, and the level are both P. So this is now again, you don't have any type, any modular tensor category which is not pointed of this type so far. Now, so we turn to the rank 6 case. This is the first example explored in such a way, and then which can also be implemented for computation, computer computation. So now, if you look at the rank 6 integral MTC, integral one, in fact, it is pointed. In fact, it is pointed. So that means it is C6 actually, C6 modular tensor category. So that means you have a quadratic form on non-degenerate quadratic form on Z6, and then you write down the corresponding way of representation. Then you write down the type. This is the type of this integral. There's only one, in fact. So 4, 2 is the decomposition, and then the level are 24 and 8. But there are strictly weakly integral one. So let me just go through it one by one. So this is level 6. So this is like type 6, level 16. In fact, this is actually a semyon together with icing. So this is actually a tensor product of 2 modular tensor categories. So what about these two? Well, they are more obscure. In fact, they are weakly integral in the usual sense, but they are also hard to determine in terms of presentation. But you can still determine it. 3, 3, there's only one type, which is level 5 and 4. And the same as 3, 2, 1 has only one type, which gives you the modular data, which is 5, 2, 1. So these types are uniquely determined. I mean, you exist in a unique way. So let's look at this one. Like C is type 3, 3, 5, 4, which is like 2, 3-dimensional representation SL2C respectively of level 5 and 4. Then actually you write quantum group notation. This is SO5 level 2. But they can also be realized. This is another one. We realize as the C5 equivalentization, a C2 equivalentization of the Tenbai-Yamagami category. So, but then you can also think of this is actually living inside the quantum double of the Tenbai-Yamagami. You take the adjoint part of the double of the Tenbai-Yamagami. But what about this? This is harder to explain in terms of quantum group. You can still do. Was Eric introduced the notion of assessing. You can assess the SO5 level 2 to get this one. But in fact, there's also a Z2 equivalentization of the Tenbai-Yamagami. Both of them are. So these two are related in several different ways. So you refer to a GNM, which is Jelaki, Nixic, and Naidu's paper. In the paper, you will see that both of these categories are there. So it depends on what your view is. There are more than one way of looking at this pair. Which one is the better way? It depends on what you're doing. But they are actually harder to decide. It's not that obvious to decide. Particularly the 3-2-1, 5-2-1 takes a hard work to deduce it. So now then you ask another question. So if I know the character of, well, we know that this is 5 and 4, so therefore it's the representation of the group SL2Z mod 20. So now if I know the character of SL2Z mod 20, can I recover C? This is the kind of question that is in my, can the character determine a finite family of modular category, even if it's empty? So this is actually the goal. Input is a character, output is the modular data of a modular tensor category. So the first thing we need to do is like, does it have a symmetric representation? So this is actually the first one we need to deal with. So yes, it is. You can always find a symmetric presentation of the character or the representation whose character is phi. So this actually the joint work with myself and Yilong Wang and my student Sammy Wilson. What we prove is the following: every representation of SL2Z mod NZ, which is the representation of finite congruent finite modular group, you can always have a symmetric representative for the representation. So that means given any character of this finite modular group, you can find a representation which is symmetric, whose character is exactly the given one. So because of general result, then the next thing is, how do we generate such a symmetric representation? Well, the result is actually also computational. So that means the proof is also generating how you can use it to generate the symmetric representation of given any maybe representation, irreducible representation SL2C. So let's go back to the theory of knob and Wolfach. So now we know what to do. So given any character, I can create a symmetric representation for it. And then now I start with a symmetric representation. So now, okay, suppose I have a symmetric representation SL2Z, which is congruent one. In this case, it doesn't matter. I just start with symmetric representation. It may not be even a representation of finite modular group. But if it's equivalent to MD representation, then automatically it has to be congruent. So there exists a real orthogonal matrix U such that they are conjugate, both S and T conjugate simultaneously. So because they both of them diagonal, then you can see that I can make both rho T and rho tilde T to be the same. Then U will just commute with both. Will just like commuting both the rho T matrix. So there's an extreme case. That's the one that I want to demonstrate as the first example, because this example will bring you to a more complicated situation. So suppose rho T has a simple eigenvalue. That means all the eigenvalue of rho tilde T is multiplicity 1. Then if I insist the rho T have the same, is the same matrix as rho tilde T, I can do it because this is a diagonal matrix. So I can just reorder the eigenvalue by using permutation. So then U will commute with this diagonal matrix. But if you have simple eigenvalue, then this U can only be side diagonal. This is actually the main reason that we create this result. So if you just side diagonal, then I just need to create decide a sign. Then I get a genuine S matrix. If it's actually realizable, that will be the MD representation that we want. So let's look at a concrete example here. You see. So I start with two inequivalent irreducible representation SL2 Z mod 5 of dimension 2. In fact, there are two of them. So I just label one of them, and then the other one is just Galois conjugate. So this is a symmetric one that we obtained from, let's say, the program we wrote to generate symmetric representations. So the other one, you look at it from this representation, they are all cyclotomic numbers. They are not arbitrary numbers, they're cyclotomic numbers. So you can always apply Galois conjugate to it, just extend your conductor, then you can apply Galois conjugate, you get another representation of SL2Z mod 5, which is not equivalent to the first one, because they change the T matrix, it will never be the equivalent representation. So you know that the Galois conjugate is another one. So then you get all of them by using Galois conjugation. Now, then this one is already distinct eigenvalue. If it's realizable, then I just need to adjust the sign. It will be a genuine modular data. So, so first of all, I know that I just up to a sign. This is already a genuine empty representation. So, but because empty representation is related to the modular data up to rescaling, then we know the dimension directly. So if the dimension is basically, because the diagonal is 1 and -1, so I know 1 over d bound to be this number, the absolute value of this number. And then I wanted the computer dimension C, then the dimension is d equal to this one. So you immediately see that this is actually the dimension of Fibonacci category. Now, how far away from the genuine modular data? It's a sign matrix. So okay, the worst is the sign up to sign. So I need to conjugate a sign matrix to the previous matrix. But then there's another choice here. So this is a matrix. I do not know which one is a unit object. So both of them could be a unit object, in fact. So let's try this. Let's say the first one is the unit object, and my S matrix is this. Epsilon is just a sign because I need to conjugate a sign. And then T is the T matrix. Now this is genuine T matrix now. Genuine means like it may not be realizable. If realizable or not, this is the one that you can get from the representation. So, but then there's something called the Frobenius-Perron dimension. So if you look at, because the first one is my dimension row, so the Frobenius-Perron dimension row correspond to the dimension row in which the term is a unit, I mean invertible algebraic number, and the absolute value is less than 1. So you can see that the absolute value of this side is the Fibonacci number. It's bigger than 1. So the second row cannot be the Frobenius-Perron. That means the first one has to be Frobenius-Perron. So because of that, this number has to be positive. So because of that, you can deduce epsilon equal to 1. This is how you determine the sign. And then you put them together. This is actually the Fibonacci category, this one, indeed. The modular data of the Fibonacci category. Now, what if I take the second row to be the unit object? Okay, I can still do, then T matrix become this. The sign become this, same as before. Now this is unit row. The Frobenius-Perron dimension cannot be in the first row because this one is the absolute value is bigger, is still bigger than 1. So that means the Frobenius-Perron dimension is still in the second row. So, but then you can see that I can see that this has to be a positive 1. This is how you get this, the epsilon equal to 1 here. I think this is -1. Sorry, make a mistake here. So this is a positive 1. The other one is negative. So what I try to say is that once you write down, you try to decide a sign, then you can use the Frobenius-Perron dimension to determine the sign of this sign diagonal matrix. So end up what you get is the following. So you start representation that we start with, and then you get 2 possible modular data. They indeed Galois conjugate. One is the complex conjugation of data. They don't look like that this way because they differ by a permutation. Because this start with 1, this one, the second row. So you just have to permute the first and second row. Then you see that the first one and the second one are differed by a complex conjugation. So what I try to say is a representation of SL2C will give you Galois conjugate of the modular data. So it may not be the whole Galois conjugate classes. Maybe the whole class of Galois conjugate, maybe half of it. So sometimes it's half of it. Sometimes, in this case, all of them. Now, this is the the first example, and I think I consider this is the baby example, and then I encourage you or any of you try this one because it should be easy to work with and should have some fun to deal with it. So now you can see that the benefit of p-example is like the high non-degeneracy of the T matrix. So what if I have a highly degenerate T matrix? That means the T matrix has a lot of repeated eigenvalues. So this is another extreme when we deal with the rank 6. So which is the type D1111. Remember that if you try to decompose them, the eigenvalue must overlap. You can see that by using the T spectrum criteria, all the ones correspond to the same eigenvalues actually. So let me give you some example here. So this is the extreme case for one extreme situation, which high multiplicity of eigenvalues. So one example is the tensor fifth bar. If you look at it, the two representation, basically previous two representation tensor together, you decompose the representation into 3 plus 1, and the level is still 5, 1. So this is one example of this type. But the length of 1 is just 1. You don't have more than 1. So this is actually real. What I mean is, if C is of this type in terms of dimension, P plus 1 over 2, and a bunch of 1, and P is a prime bigger than 3, and the order of T is P, this is the result published in the paper, then C can only be of this type. That means the length of 1 can only repeat only once. You cannot have a lot of ones. So in this case, well, it depends on P is congruent to 1 mod 4 or 3 mod 4. If congruent to 1 mod 4, C must be self-dual. That means the modular data must be real, all real. And otherwise, C is not self-dual. That means you have the complex term. So then you look at the case of rank 6. Then you can eliminate field types by this result. You can eliminate 3, 1, 1, 1, 4, 1, 1. Okay, the level 5, 1, 1, and 7, 1, 1. So it doesn't matter. They don't show up. So because like I just need it to be P, so I need to have the levels. They are multiple of P. Oh, I mean they are divisor of P. Sorry. Okay, so this is the highly degenerate case. So now we go back to a simpler case. So again, this is the beginning of the adventure. So we try to do something simpler at the beginning. Hopefully we evolve to something more depth. So we deal with the representation. Let's start with some representation. They are non-degenerate. Non-degenerate means the multiplicity of each eigenvalue is 1, so they don't repeat. So we have a lot of these irreducible representation of SL2C, particularly in small rank. So for example, you look at the irreducible representation SL2C mod 5 of dimension less than 5 are all non-degenerate. In fact, any irreducible representation of dimension less than 5 of SL2Z, in fact, is non-degenerate. But this one can be obtained by observing the example directly. But when you go to higher degree, it could repeat. In fact, depends on type of reducible, it could repeat quite often. The multiplicity could be high. So why do I want to do that? Because I want to deal with some reconstruction of direct sum of two non-degenerate irreducible representation. So I start with two non-degenerate irreducible representation SL2C mod n, such that the direct sum of these two irreducible, well, that's not necessarily irreducible, just non-degenerate. The direct sum is equivalent to an empty representation of rho for some MTC. Then we can actually write down the modular data for this case, if the intersection is just one element, the intersection of these spectrum is one element, and the dimension rho I has to be bigger than 1. Or the other case is we can completely solve the modular data. Well, they may not be modular data, but we can write down the corresponding empty representation for these cases. If rho 1, the spectrum of the first one is a subset of the spectrum of the second one, and they have opposite parity, we can also write down the empty representation for this direct sum. Well, when I say empty representation, it means potential empty representation. But end up they may not be realized. So let me just illustrate a little bit of how we use the result. So for example, rho tilde is a direct sum of these two irreducible. What are they? Well, this convention is used for the paper. This is a 4-dimensional representation of level 7. So the one is just some Galois orbit indicator, the first one. And this one is also, there's a 2-dimensional representation of level 3, and it involved the one representative of the Galois orbit. And then this 0 means you tensor some scalar to it. I mean, 1-dimensional representation SL2C. So that means I don't tensor anything. That's what it means. So anyway, just some representation. The main term are these: dimension 4, level 7, and the other one is dimension 2 or level 3. Then you put them together. The T matrix will be just put together. So these 4 are the 7th root of unity, and these 2 are 3rd root unity. So then I form a new representation now. But look at this, their spectrum, each of them are non-degenerate. Their spectrum only overlap once. So according to the result, I can be able to write down the empty representation associated with this one. So indeed, you can just write down, again, up to a sign. So now it's closed. If either this one is not realizable or it's the genuine one, up to a sign. So how can we define the sign, determine the sign? Same as before. We pick well, these 2 are the unit row now. These 2 are the only because they have zeros. So these 2 are the only possible unit row. So I try both of them, and then you can see that by using the dimension, you can see that the Frobenius peron and the unit object are distinct, in fact. So they cannot be. That means like one is unit, the other one is Frobenius peron, and vice versa. So you can use it to determine the epsilon and end up solving the whole modular data by use. This is a empty representation. You have to rescale this one basically. I mean the first term, the 1 term, or I mean these term. And once you rescale it, it will be the modular data. Then you can see that these 2 possibly are indeed the Galois conjugate, the modular data of G2 level 3, again coming from a quantum group. So I just show you that those which are possible, those are impossible that takes more time to eliminate sometime. So then I show you some extreme case. This is the one that is quite extreme in the following way. So again, now I have 3 of them put together, dimension 3, level 4, dimension 2, level 3, dimension 1, level 2, put them together. So I get a representation of this, and the diagonal will be this. Now I want to subdivide into 2 parts. Basically, I divide into this first 3 and then the sum of the rest of 2. So now you can see that now each of them is non-degenerate, but the overlap is 2. So you have 1 and the 1 and the -1 and -1. So instead of 1 pair of overlap, you have 2 pair overlap, but you can still solve it. you just like build on the one that has a single pair of overlap to solve further for this double overlap case. So you can still solve it. And then you can write down the S matrix for it. So this is the S matrix for this system. Still uniquely solved, basically. Now, the D is given by 2 times square root 3 minus 3. It looks like everything is fine. I solved the whole modular data. But wait for it. Well, when you say it's solved, that means whatever, well, not whatever, many property of the modular data are satisfied by S and T. So then we go further, which is using the Verlander formula to write down the corresponding fusion rule of the modular category. So, and then well, and then you can pick. Well, maybe I just show you how it works. So then I pick the 5th object in my system. So for example, I mean, then I compute the indicator using indicator form because I have everything. The second indicator is given. I have T already. So that means I have theta. I have the D already because I can choose which unit row it is. In fact, the Frobenius spheron and the unit row are distinct in this case. So pick one, then the other one is good. So pick the unit object, and then the other one would be the Frobenius spheron object. Then you compute the second indicator of the 5th object. You get a 2 here. Now, this is, as I said, this extreme case. That means it almost satisfies everything except that the second indicator. Well, in theory, if this is a modular tensor category, this formula will work, and this should be a plus or minus 1. It cannot be 2. So this is the only contradiction that we get for this modular tensor. This is a very extreme case. It takes a long way to get to here to get the indicator 2. But actually, there's some question that, although it is not a modular tensor category, but it may form a ribbon category or even a fusion category. So that means the fusion matrix itself may form, it's certainly form a C-based unital ring, but whether it can be categorized is not clear. But anyway, we did not inspect further. We only know that this one cannot be realized as a modular tensor category. So I show you a few examples of different degree of difficulty to solve. One is easiest. The second one is a little bit more complicated. The third one, it probably is the most tedious one, which is not working. So, but then you can do it across the board. That means you pick any rank 6, you just use the partition to write down all the possible dimension, decomposition, and then fill in the corresponding level, and then you go through it. So for rank, for anything of type, which is not type 6, we did it by hand. For type 6, like you can just inspect the representation directly or go through the computer program. Both of them are quite direct. So after all this, we basically find out that these are all the possible types, and the corresponding they are realized by certain quantum groups, modular tensor category. The most extreme one I would say is this one. This is the only rank 6 modular tensor category which does not have a unitary or pseudo-unitary Galois representative. So this is actually not unitary. You cannot unitarize it because the Frobenius spheron orbit and the unit orbit are separate. They're distinct. So you never be able to conjugate to a one with pseudo-unitary category. So the conclusion is nothing new for the rank 6. They all known in a sense, but at least we complete the list. That's all we have for rank 6. No new modular data discovered for rank 6. Now, then what about rank 7 and rank 8? So these higher rank, we mainly use computer programming so far. For rank 7, we know we have a classification for integral one. For rank 8, we did not. So, but rank 7 is a little bit easier because 7 is a prime. You cannot factorize it further than the dimension. So for 8, it's more daunting. I mean, so we certainly need a lot of computer power to do it. But so far, what we get is that still nothing new for non-integral modular data. The most extreme one that we found could come from, which is also the case in rank 6, which is the double Lie group, and then you have one modular subcategory of the double of the Lie group is the one of type 3, and 5, 4, and so on. And this is also the case. This time it's not double of Tenbai Yamagami. It's the double of the Lie group of the abelian group C5 with coefficient 5. Inside there, there's a decomposition, and then, or you can say it's the adjoint subcategory, which is the modular data of rank 8. This one took us a while to realize that, but end up we realized it. All of them are this type. So the integral one, we haven't pinned down the complete list yet. So this one we need some strategy to figure out. Either theoretically deduce the integral modular tensor category rank 8 directly, or we design some criteria for computer search. So we haven't have a right strategy to deal with it yet so far. So we only knew some candidate. For example, the omega S3 is of this kind, but there are some other plus 2 other. They are not group theoretical, but very much like this. And the other one is like a C, of course, the abelian group Cn, maybe center G solid. Well, these are the candidates that we know, but we do not know these contribute to all of them so far. But that's what we have. Thank you for extension. I think roughly a time.
Okay. Thanks for the great talk. Let me stop recording.